So this video will work through the equations for chapter 6 on work and energy. The first two chapters, 1 and 2, that you've now completed were really just review chapters, and they covered material that you should have known from previous physics courses. But you will need that information to continue on in these later topics in the course. So you've seen the video of the concepts of work, how you have to have a force working to do work, and you will also look at some more videos on examples of doing calculations for work and energy. And for this chapter, it's just kinetic energy that we're talking about. So I'll work through the chapter 6 key equations that you should have in front of you. You can either look at them on D2L or print them out. And the first equation that is on that sheet looks like this. So we define these quantities: work in joules. Remember, that's a scalar quantity, positive, negative, or zero. And it's very significant whether the work done by a force is positive, negative, or zero. If it's positive, that means the force is trying to speed the object up. Now, whether it's successful or not depends on all the other forces that are acting. But if a force is pushing in the direction something's going, it will be doing positive work. If work is negative, that means the force is trying to slow the thing down. And most of the time that's friction, but it could be somebody literally pushing in the opposite direction that something's moving, trying to slow it down. It is possible also to have zero work. So if a force is neither trying to speed it up or slow it down, but pushing perpendicular to the way it's going, it's not doing any work at all. Okay, so F is force in newtons. Now notice how work is a scalar quantity, force is a vector quantity, but so is displacement. So this F refers to the magnitude of the force in this equation. The S refers to the magnitude of the displacement. Now sometimes this S is replaced with a delta X. So depending on the video or the example, you may see a delta X instead of displacement. And so in order for work to be done, the object has to move. So if you're just standing there holding something, no matter how hard it is, if it's not moving, technically there's no work done. Now the phi is important. This is the angle between the force and the displacement. The force is vector and the displacement is vector. So if the force is off like this and the displacement is like this, then there's the angle phi. Okay, so that's the first equation. Now, remember I talked about the dot product. We can write that in a much more succinct method by using the dot product. And that dot product gives you all this information that I gave you up here. The dot product tells you that if these things are in the, if the force has a component in the direction of S, the work's going to be positive. Component is opposite the direction of S, it's negative. Perpendicular is zero, because the dot product has all that information in it. Okay, so we usually don't just calculate work for something to do. We usually calculate it to relate to changes in kinetic energy. So we're going to need the definition of kinetic energy. We're going to see there are many forms of energy. In this chapter, we'll just worry about kinetic energy. The next chapter, we'll worry about potential energy. So your book just uses a K for kinetic energy, 1/2 mv squared. I like to use KE, but this is fine. So K is kinetic energy. And remember, you're writing these things down in your notebook because you're going to need these when you go to do the problems in Mastering Physics. You're also going to need to take a picture to show me that you've actually done this. So K is kinetic energy in joules, M is mass in kilograms, and V is just speed, not velocity, just speed, just whether it's moving or not, doesn't matter which way it's moving, in meters per second. Okay, so something has kinetic energy if it is moving, period, end of story. If it's not moving, it doesn't have any kinetic energy. The bigger the mass, assuming that two objects have the same speed, the bigger the mass, the more kinetic energy something has. Okay, so now it's called the work energy theorem, the relationship between work and kinetic energy. So the way your formula sheet does it, it says W total K2 minus K1, which is delta K. Now I like to use W net. This W total means the net work done. It means you have to add up the work from all the forces, and that's in joules. Now, it's much easier to add up all the works because they're scalar quantities than it is to add up all the forces to get the net force. But if you like adding up vectors, then you could use that the total work done would be F net dot displacement. But this would require a vector addition, and usually vector additions are not nearly as easy to do as scalar additions. So beware of using that form. Now, K2 minus K1, it's actually final minus initial, but delta K, we'll just say, is change in kinetic energy. Okay, so it's very important that it's the change. So either it's going to speed up, slow down, or not change at all, in which case there's no net work done. Doesn't mean there aren't any forces. You could have forces, but they're just, all the forces cancel out, so the object neither speeds up nor slows down. Could still be moving though, just no change in kinetic energy. And there'll be some examples of using that equation on the videos and the examples you do in Mastering Physics. Okay, now another thing you have to be aware of, if you have an object being pushed by a constant force, so you have a 10 Newton force and the thing moves 5 meters, and if the force is constant the whole time, now the thing will speed up, but if the force remains the same, then the work is constant, and you just take force dot displacement, and in this case it'd be 50 newtons, 50 Newton meters, which is joules. But the force isn't necessarily always constant. The force may be changing. So for example, if you had the force was 10 newtons, and then a little while later the force dropped to 5 newtons, and a little while later maybe dropped to 1 newton, and then each one had its own displacement, say it acts for 1 meter, 1 meter, 1 meter. Well, to get the work done, you would have to add all these things up. You would have to go 10 times 1, plus 5 times 1, 1 times 1, to get the net work. Now, if this force happens to be changing smoothly, this is when the sum becomes an integral. So the integral of f dx, I'm going to go fx, that's the x component. So this is the next equation on the formula sheet. We need to understand how this equation works. Okay, so what this means is it's like that picture above, except the dx is just a tiny little bit of displacement, and the fx is changing as it goes. It's some function of x. And so it may get bigger and bigger, and then it might get smaller again. But for each little tiny piece of displacement, you have to add what the force is times the displacement, what the force is times the displacement. That's what an integral is. See that sign? It's an S for summation. So add up what the force is at every point on the x-axis, multiply by that little bit of displacement on the x-axis, and then add it all up between x1 and x2. So x1 may be here, x2 may be over here, and you'll get the total work done. So this is a great equation for springs, for example. If the force due to a spring, when you is negative kx, then when you put that into the formula, the work done is negative kx dx between x1 and x2. That's 1/2 kx2 squared minus x1 squared. That would be the work done if a spring is pushing on a mass as it moves between x2 and x1, where k is the spring constant. So it's this force in here. Often it is from a spring, which we know the formula, negative kx, Or sometimes they'll just give you a random function. You just put it in and integrate. Okay, now that is well represented on a graph. If you graph the force in the x direction as a function of x, and you get, say, some function like this, then the integral between x1 and x2, we know, is the area under the curve. And this area represents the work done. So if you happen to know the equation for the force, fine, you put it into the integral and you integrate. If you happen to know the picture for the force, you can like geometrically work out what this area is and you'll get the work done. That area, remember, would then be, as long as there are no other forces, that would also be the change in kinetic energy. Okay, the next concept in this chapter has to do with power. So power, average power, is the change in the work, or it's the rate at which work is done. So this is rate of work done. Remember, anything that's a rate means per time. The units for power are watts. And that means that a watt, by definition, is a joule per second. Okay, and so the delta T is time. So if you run up a pair of stairs really quickly, you would be generating more power than if you go up slowly, even though the amount of work done would be the same in both cases, because the force it takes to lift your body would be the same. Now that's average, which means assuming that the work done is just a constant and you simply have that number, you can use this formula. But if the work is variable, or if you just want instantaneous power, like just during a sprint or something, then the power instantaneously is the derivative. So this would be instantaneous power. And that's the derivative of work with respect to time. Now, you can see where we get this last equation on this formula sheet. If I put that the work is the force dot displacement, and if I take out, remember it's an instantaneous force, so force is constant over this particular instant. Take that out, you go dot, and I've got ds dt, which is velocity. It's force dot velocity. Okay, and that's also power. So instantaneous power is force dot, and then this is velocity. And so if you're, say, traveling along in your car at a certain velocity and you put your foot on the gas, the power needed by the engine would be the force that's exerted from the engine dotted with your velocity. And obviously those things in a car, those things are mostly parallel. Okay, so that takes care of the equations for chapter 6. You can now go on and do your Mastering Physics assignment. And remember, in the assignment, the solutions are always given to you in full detail after you've attempted the question. So you may want to write those solutions out if you get the question wrong, or watch the little video that comes with it.